Our second speaker of the morning is Olivier Zindy, who will be telling us about Poisson-Dirichlet statistics for extremes of the 2D Gaussian.
Thanks. So let me first thank the organizer for the opportunity to give a talk to this nice conference. So in this talk, I want to study the extremes of the 2D discrete Gaussian free fields by considering the Gibbs measure. But before starting, I want to mention that recently there were a lot of progress about these extremes using branching random walk approach. But in this talk, I will not use branching random walk techniques, but I will explain how we can apply spin glass techniques. And this is a joint work with Louis-Pierre. So the plan of the talk is the following. First, I will describe the model and recall previous results. Then I will state the two main results. First one is that the 2D discrete Gaussian free field belongs to the one-step replica symmetry breaking. I will explain that in detail. And then I will explain how we can deduce from this result that the Gibbs weights converge in a suitable sense to Poisson-Dirichlet weights. And then I will try to give ideas about the proof. So this Gaussian free field dimension 2 was introduced this morning, but let me quickly recall one definition. So a Gaussian free field on a box A with Dirichlet boundary condition is just a center Gaussian field with covariance given by the green function, which is defined like this. So you start a random walk, a simple random walk at site V, and you count the number of visits to a site V prime before exiting the box A. In this talk, I will consider the following box, which is just a square of side length n, or small n here. And I call it Vn. And then I introduce a subbox like this, containing all points at distance larger than delta n for some delta between 0 and 1. And if you take, for example, the book of Lawler and Limich, you have the following estimate for the variance. So if I will call this Vn delta, which is this blue subbox, the bulk. And if we have this uniform estimate in the bulk. But let me mention that in fact this quantity is also an upper bound for the variance in the full box Vn. And then we have this estimate for the covariance between 2 points V and V prime. So here we see the logarithm of the, I write n squared is the logarithm of n squared. So we could write it 2 over pi times log n, but n squared is the number of points in my big box, so I prefer to write it like this. And that's why we call this field a log-correlated Gaussian field. Okay, so the first result was already introduced by Nicolas this morning. It's about the leading order of the maximum, and it was this result was proved by Bolthausen, Döschel, Jacomin, and says that if you take the maximum and normalize it by log n squared, then you converge in probability to some constant which is square root of 2 over pi. The idea of the proof is to approximate this Gaussian field by a tree. And when I mean tree, what I mean by tree is not a branching random walk, but a tree with k levels where k is large enough. And this first order is already the same as for the random energy model, which is a very simple model. It's just n squared ID centered Gaussian random variable with variance 1 over pi log n squared. And this technique was refined by Olivier Davio, who computed the log number of I points. So what is it? You look at the number of points in the bulk where the field has a value larger than the first order of the maximum times some lambda between 0 and 1. You take the logarithm of this, normalize it by log n squared, and at the limit you get 1 minus lambda squared. And this convergence holds in probability. And again, it's exactly the same as if you do this computation for the random energy model. Okay. So now I want to explain how we can deduce from this. It's very easy to deduce the free energy. And it is, again, the same as for the random energy model. So first, I introduce here the partition function, which is the sum over all v in my big box of e to the power beta times the value of the field at side v. And then I denote by fn of beta the free energy, which is the logarithm of this partition function, normalized by log n squared. And what we get is that the free energy is again the same as the REM, so we get this convergence. This quantity converges to some f beta. This convergence holds almost surely and in L1. And we have some critical beta, which beta stands here for the inverse of the temperature. And we have this phase transition, like for the random energy model, which was also explained this morning by Nicolas. So the proof is very, very easy. Okay, first observation is that it's trivial, but it will be very useful later in the proof. So this free energy is differentiable at all beta. And the proof is just to apply Laplace method. So for the lower bound, what you do is that you say, okay, I know the first order of the maximum, I know the log number of high points, so I rewrite this sum as an integral over lambda, and then I apply Laplace method, and I obtain the good lower bound. For the upper bound, we just apply Jensen inequality, and compute the expected number of high points, and you just need to have an upper bound on the variances, and that's enough to conclude and get the same upper bound as the lower bound. So that's straight direct corollary from the previous results. But this point here is very important. Okay. So what is our main result? We want to study the overlap distribution. So first, I introduce the Gibbs measure. That's a random probability measure on my box Vn, defined like this. To a side V, I associate the following weight, e to the power beta times the value of the field at side V, normalized by the partition function. And then I want to introduce an overlap. So I can define it like this. I associate to V and V prime the overlap defined by the covariance between phi V and phi V prime, normalized by, let's say, the variance in the bulk, which is 1 over pi log n squared. Okay, that's the definition, but if you want to relate it with the distance in my box, because of the estimate and the covariance, we can rewrite it like this, and it's 1 minus the logarithm of the distance squared, normalized by log n squared. So there is, if V and V prime are very close, this is close to 1, and if V and V prime are at a distance of order n, this is close to 0. So the first result we obtain is that at low temperature, that means for beta larger than the beta critical, we have this result. So in fact, what we consider is the first V1 and V2 are 2 points sampled independently according to the Gibbs measure, and then we consider the cumulative distribution function associated to this overlap. But I will not repeat it each time, and I will say overlap distribution. And what you get at the limit is that the limit is this one. Either this overlap at the limit is 0 or 1. That's why we say that the Gaussian free field belongs to the one-step replica symmetry breaking class. So it means that if you sample 2 points, either they are at a distance, they are very close, or they are at a macroscopic distance. What I mean by that is that here it's smaller than n to the epsilon for all epsilon, and here it's larger than n1 minus epsilon. And it's consistent with the result obtained by Ding and Zaitouni, which say that if you consider 2 points, or if you consider points close to the extreme value, they are either at a distance of order 1 or at a distance of order n. Okay, this was proved for the branching Brownian motion by Derrida and Spohn. Also, the branching Brownian motion is a hierarchical model, and I think Nicolas already said a few words about that. And it was conjectured by 2 physicists, Carpentier and Le Dussal, in 2000. Okay. So now the second result is about the Poisson-Dirichlet weights we get at the limit. So I will quickly recall what I mean by that. So we fix alpha between 0 and 1. We consider, or we introduce the eta I, which are the atoms of a Poisson point process on the positive half line with intensity s to the power minus alpha minus 1. And then a Poisson-Dirichlet variable psi of parameter alpha is just a random variable on the space of decreasing weights, which sum is less than 1, and which have the same law as the eta I normalized by the sum and reorder in a decreasing way. So the second result you obtain is the following. So it's a bit heavy, but so we still pick beta larger than beta critical. We denote by psi a Poisson-Dirichlet variable of parameter beta c over beta, which is strictly smaller than 1. And then we have this result. So what we do here is that we consider S replicas. What does it mean? We sample independently according to the Gibbs measure S points in my box V1, Vs. I associate all the possible overlaps QVL, VL prime. What did I write here? Okay. And we put them in a matrix. By convention, QVV is 1. And here I have QV1, V2, QV1, Vs. And by definition of the overlap, this matrix is symmetric. Then I want to apply a continuous function to this. And that's why I define f on this space, because it's symmetric and we know that there are 1 on the diagonal. So here it means just that we sample the point according to the Gibbs measure, then you take the expectation, and what you get at the limit is this. So it's not surprising that you get Dirac function here, because at the limit the overlap are 0 or 1, and here you see that the Dirichlet weight appear. If you want to see more precisely the convergence, we should rewrite the left-hand side term like this. If you write the left this term like this, you can see that the Gibbs weight converges to the Poisson-Dirichlet weight. So we don't obtain, with this approach, we do not obtain the convergence of the Gibbs measure, because we consider only test function applied to overlap matrices. And this result was conjectured by Fyodorov and Bouchot in 2008. And now I want to mention that Madol, Rod, and Vargas obtain a precise description of this Gibbs measure for the Gaussian multiplicative curve, which is a very nice result. And this result is related to the study of the extremal process by Biskup and Louis-Dor. But if you want to understand the Gibbs measure, you need some information about the decoration. And according to what I know, we do not know everything about the decoration right now. Okay. So now I will try to explain the proof. So first I want to explain how we can apply recent spin glass techniques to prove that the first theorem implies the second one. So the first is to say, okay, we can apply concentration result by Panchenko, which says that if the free energy is differentiable, then we have this concentration result. And then, applying Gaussian integration by parts, we obtain the so-called Ghirlanda-Guerra identities. So I should maybe explain a little bit this. So let me rewrite my matrix. D2. So in this term I sample S points. I have S replicas, but here I have S plus 1. And in fact, what we want to understand here is the conditional expectation of this guy with respect to the sigma field generated by this matrix. And what we obtain is that with probability, so here we sample S plus 1 point, and now we can also consider this matrix, and what we can see is that with probability 1 over S it is independent, and with probability 1 over S it is equal to one of these guys. Okay, so now how can we deduce from this that we have Poisson-Dirichlet weight? So the first thing is to find a good space of convergence. I don't want to give too much details, but it's the space of infinite covariance matrices. And because of compactness, we can consider, we can work with a converging subsequence. And because of weak exchangeability, we can apply Dobby-Sudakov representation theorem that says that there exists some random probability measure that I did not hear by mu beta on some abstract Hilbert space H, such that the following holds. So at the limit, you get a Gram matrix associated with vectors sampled independently according to this mu beta. Okay, so now if you use the first theorem, what you obtain is that you just have to approximate this indicator function by continuous function. And you see that you have, again, a jump at 0 and a jump at 1. Or an atom at 0 and an atom at 1. You can also take the limits in the Ghirlanda-Guerra identities, and the error term disappears, and you obtain this relation for this mu beta. Now, if you combine both results and make a good choice of the functions f, you can deduce that mu beta is atomic. So it means that there exists some random weight psi I that sum to 1, and orthonormal vectors ei such that mu beta can be written like this. And now we would like to prove that the psi I are Poisson-Dirichlet random variables. So if again you use the Ghirlanda-Guerra identities but with another choice of function f, you obtain recursive equation on the joint moments. Joint moments associated to the psi I are defined like this. So you obtain recursive equation, and in fact this recursive equation characterizes the Poisson-Dirichlet weight. So that's the idea, to prove first theorem from the second theorem from the first one. Okay, now I want to explain how we prove the first theorem. So we want to sample points according to the Gibbs measure in my full box. But we have problems because the green function tends to 0 when the point V, for example, the variance tends to 0 when V tends to the boundary. Or if you fix V and makes V prime tends to the boundary, again it tends to 0. So both the variance and the covariance get closer to 0, closer you get to the boundary. And that's a problem if you want to use comparison argument. So we want to sample points according to the Gibbs measure. The first idea is to say, okay, I will just work in that box and probably this part is negligible. But in fact, that's completely wrong because a point here has the same variance as a point here, and you have the same number of points here than here, or same order of number of points. So the idea is to consider a larger box and consider the points that are a distance larger than n to the power 1 minus rho, with rho between 0 and 1, distance with respect to the boundary. So this box is really larger than the bulk. And in fact, if you consider this box, you can prove that the Gibbs mass associated to its complement tends to 0 in probability. So now we can just consider this red box. And that's enough to avoid the boundary effect. And I will try to explain that. So now what we want to understand the overlap distribution of the Gaussian free field. The idea, that's if you want to make computation on this object, it's difficult. So the idea is to introduce another model, more complicated, that we will call a perturbed model, and such that the overlap distribution is related in some sense to the free energy of this more complicated model. Then you compute this free energy, and then because of the relation between its free energy and the overlap distribution, you can understand the overlap distribution. So what we do here is, as was explained by Nicolas, we will consider first some scale decomposition. So to a point V, we'll associate a box here. So that's V. We consider a box of psi length 1 minus alpha. And we write, okay, that's a property of the Gaussian free field. We denote by 5 a new field associated to boxes. So this field is defined like this. Phi associated to the box V alpha, that's this box centered at alpha, is given by the conditional expectation of my initial field at side V with respect to the sigma field generated by the complement of this green box. And by the Gaussian free field property, it's the same as the conditional expectation with respect to the sigma field generated by the boundary. And then, because the GFF, the discrete GFF is a Gaussian vector, you can write it like this, and you have two independent terms. So that's what was explained by Nicolas. And the idea to introduce this perturbed model we need is to put weights, different weights, in front of these two terms. So here in this general case, I denote them by sigma 1 and sigma 2. Oops. Sorry. So the first, and what we choose is, so we pick alpha between 0 and 1, my scale, and then I will make the following choice. First, I choose sigma 1 equal to 1, and sigma 2 equal to 1 plus u, where u is between minus 1 and 1. It's important that you consider also u negative. I give a name to this quantity. Okay, right now I don't know that it's converges, but let's work along the subsequence. I give a name to this limit, x beta r, and here I introduce the free energy associated with the Perture model psi, this psi here, but restricted to my red box here, so that I can avoid the boundary effect. And the relation between the free energy of the Perture model and the overlap distribution of the Gaussian free field is given by this. So let me assume that I am able to compute the limit of the expectation of this, and that I have an explicit expression. Then the relation is the following. Here you have this limit, you take the derivative with respect to u. You can think of it as a perturbative parameter, and then you make u tends to 0, rho to 0, and what you obtain is the integral from alpha to 1 of this guy you want to understand, times some constant beta squared over pi. Because x beta of r has nice properties, you can deduce from this relation the explicit expression for x beta of r. To prove this, you use Gaussian integration by part, convexity arguments to exchange all the limit and the expectation and the derivative here. And what is important for the Gaussian free field is to be careful with what we do closer you get to the boundary, because you want to relate when you apply the Gaussian integration by part, some covariance appear, and you want to relate it to the distance, but the relation with the distance is clear in the bulk, but here it's not that easy. So you need to be very careful when you get close to the boundary. Okay, so now I have 20 minutes to explain how we compute the free energy of this Perture model. So first, I will introduce the free energy of a more general RAM. So I change 1 by sigma squared here, and I denote its free energy by f beta sigma squared. So here I have an explicit expression, and it's very easy to compute this free energy. So if I take rho smaller than alpha, why do I do that? Such that for all points in my red box, this ensures that for all points in my red box, the green box will be included in Vn. So if I consider let's say u conditional expectation with respect to the green box in V, I can say that this guy indexed by u in my green box is again a GFF restricted to this green box. And what we obtain is that the free energy of the Perture model is the same as for the Derrida's generalized random energy model. So I want to define this. So remember that I have alpha between 0 and 1, and first I consider n 2 to the alpha random variable, which are iid and 0 alpha over pi log n squared. And then to each of them, I associate n to 1 minus alpha random variable that are iid, independent for the random variables at the first level, and that have this variance. So at the end, if you have a point, let's say V here, you associate a Gaussian random variable which is just the sum of this one and this one. So at the end, you have this times this, so n to the power 2 points on your tree, and the variance of each of them is the sum of both variances, so it's 1 over pi times log n squared, and you have this hierarchical structure for the correlations. So it's not too complicated to compute for this guy the leading order of the maximum, the number of high points, and its free energy. And in fact, this Pierre model, at least at the level of the free energy, can be approximated by these two-level gram. And the result is the following. If sigma 1 is smaller than sigma 2, then you have the same free energy as a random energy model. And if sigma 1 is larger than sigma 2, then you have a linear interpolation between the free energies of two different random energy models. That's what happens for these two-level gram. And it is the same here for the Pierre model. So now, since we know that and have an explicit expression here, we can compute this explicitly, take the derivative, and know this guy from which we deduce theorem 1. So the last step is to compute the limit of this expectation. The first thing is the lower bound. So the lower bound, it's not too difficult because you can restrict your attention to my blue box, Vn delta, the bulk. That's enough. And then you just repeat what Bolthausen-Döschel-Jacomin did. Oh, no, we don't need that, in fact, because we just need an upper bound for this maximum. So that's very easy to obtain. The hard part in the Bolthausen-Döschel-Jacomin work was the lower bound. So the first thing, we want to write this as an integral over the gamma I points, and again apply Laplace method. So first we need to understand the good order of the maximum, but we only need an upper bound. And we obtain this, where this gamma max is defined like this. So here V12 was defined here, and if sigma 1 is larger than sigma 2, we have this expression for gamma max. So people studying non-homogeneous branching wave motion or branching random walk should not be surprised, because this is the leading order also in this case. So the proof is very easy. If sigma 1 is smaller than sigma 2, you behave like a random energy model, so it's enough to apply a union bound. And if sigma 1 is larger than sigma 2, then you need the correlation structure and have to make a comparison with a two-level gram. So you want to compare with an object which has the same variance structure, but which is less correlated. And since you are in the bulk, you have a uniform estimate for the variance, and you can just make a comparison with this two-level gram, restricted to this bulk, and apply Slepian's lemma, for example. Okay. The second step is to understand the log number, or not the log number, but the high points. The high points, so I define here what are the high points. It's the number of points in my bulk where the field has a value close to the first order of the maximum times gamma. If I put a larger here, it's the same. And what we obtain, let me introduce this expression. If sigma 1 is smaller than sigma 2, 1 minus gamma squared divided by V12. And if sigma 1 is sigma 2, we have two expressions depending of the value of gamma, depending on the value of gamma. And sorry? This one? It's a definition. It's for it's a definition. It's the yeah. It's the exponent for the number of I points. So now we have, in fact, this is the good bound, the good estimate for the long number of this guy, but we don't need this. We just need an upper bound, and this is a good good upper bound. So for any gamma between 0 and the good order of the maximum, and for any e smaller than this guy, then we have this. This gives you the good upper bound in this following sense. This probability tends to 0, and we even know that we converges at least with this speed. And in fact, we don't have to work that much because Davio was able to understand the log number of I points for the GFF by comparing, which is the same as for the random energy model. So here we know that, well, we believe that we can compare this Perture model with the two-level Graham. So we apply the same kind of techniques, but repeat it twice at the two levels. Okay, and then it's very easy. You just write this as an integral. It's almost that because here I don't consider the negative value, and then you apply Laplace method, and you get the good bound, lower bound. For the upper bound, it's more complicated because you want to compare this model, this Perture model, with a model which has the same variance structure, but closer and closer you get to this boundary, smaller and smaller is the variance, but also the covariance. So you would like to apply something like Kahn's convexity inequality, but you cannot because this guy is less correlated, but the variance here is larger than what you obtain here close to the boundary. So you cannot do it like that. So what is the idea? It's just to say, okay, divide this red box in boxes of side length n 1 minus alpha, let's say divided by 100. Just a convenient choice. You have to constant large enough here. And then what happens is that we will introduce a new two-level field, two-level correlated field like this, but where the first level, the random variables are indexed by this box. And what we want to do is that at the first level, we want to give the same contribution to all the guys, all the sites in such a box. And then at the second level, we will associate to them independent random variables. So let me focus on such a box, and what you see is that if I consider 1 point V here and 1 point V prime here, and if I draw the green box, associated green box, I get something like that. And what you see is that because of this constant here, the intersection here is big. And in fact, what you can say is that these two guys, so that's the green box associated to V, conditional expectation, the field at the first level, and the field associated at the first level associated to V prime. Are very close. That means that the L2 distance between both is of order 1. So in fact, that's enough to say, okay, I can associate at my first level the same contribution for all the points in this small box. And then at the second level, you associate independent random variable. So you get something less correlated. But what is that field? You don't get this picture because the contribution at the first level has a variance that tends to 0 when you tend to the boundary. So what you get is something like that. At the first level, that's what you obtain in the bulk, but outside, closer and closer you get to the boundary, smaller and smaller is the variance. So you get something like that. And then again, you can, it's not too complicated to convince yourself that the contribution at the second level are IID. Oh, okay, have the same variance. So you can compare it with a field which has this structure. Then you have something which has the same variance structure but is less correlated. So you can apply Kahn's convexity inequality to say that the expectation of the free energy of the Perture model is less than the expectation of the free energy of this non-homogeneous generalized random energy model. And what happens then is that using Gaussian integration by part, you can convince yourself that if you increase the variance of the random variable here at the first level, you increase the expectation of the free energy. And you do that, and then you get as an upper bound the free energy of the two-level gram I introduced before. And in fact, it's the good upper bound which matches with the lower bound. So this gives us the ID for the lower bound. And now I want to mention, I want to talk about many results and speak about a little bit about universality class. So as you could see, everything what we obtain is the same as for the random energy model. So the natural question is to say, when do we feel the correlation? And so first I want to speak about branching random walk and branching Brownian motion, and then I will explain at which level can we feel the difference with the REM for the Gaussian free field. So it was already explained by Nicolas this morning, but I will repeat this a little bit. So Bramson and for the branching Brownian motion and Heidekon for the branching random walk prove that in fact, if you want the good centering term has a different the second term in the centering term is different. That's why you see the 3/2, the famous 3/2 appearing, and both of them prove that this center maximum converges with this good centering term. And the limit is no more Gumbel, but it's a randomly shifted Gumbel distribution. And then there was two teams, Arguin-Bovy and Kistler on one side, Heidekon, Berestecki, Brunet, and Shi on the other side for the branching Brownian motion, and Madol for branching random walk, who studied the extremal process, that's the full process here, seen from the good order for the maximum. And what they obtain, it's no more a Poisson point process, but it's a Poisson cluster process, or a decorated, also called decorated Poisson point process. So this branching random walk, if you start looking at the second order of the maximum, or the limiting law, or the extremal process, you can see that branching random walk and branching Brownian motion do not behave like the random energy model. And now what about the non-hierarchical case? So for example, the 2D discrete Gaussian free field or the Gaussian multiplicative cow. So it was a conjecture by Fyodorov and Bouchot that the extremal process should be the one of the, Carpentier-Lutzel first and Fyodorov-Bouchot after that, but the external process associated to these fields called log-correlated Gaussian fields should have the same behavior as the one of the branching Brownian motion. And so what are the results about the 2D discrete GFF? It's the same as that mentioned by Nicolas this morning. So the first paper, which is a very, very nice paper because you can already see these three approximations, is the work by Bolthausen, Lösch, and Jacomin. Then Davio refined the techniques. Bramson and Zaitouni proved the tightness. And Ding and Zaitouni, that's what I mentioned about the distance between 2 points close to the maximum. So Ding and Zaitouni studied the set of near maxima. Bramson, Ding, and Zaitouni obtained the convergence of the recentered maximum. And more recently, Biscup and Louis-d'Or are working on the extremal process. So if I understand well, but they understand the behavior of the local maximum, but I'm not sure they have the decoration. In this case, that means the geometry close to this local maximum. But I think it's ongoing work. And so a second class of model is the Gaussian multiplicative cow. So I should mention the work by Duplantier, Roche, Sheffield, and Vargas, who studied the measure, the measure at criticality, and introduced the so-called derivative martingale for the critical Gaussian multiplicative cow. Madol studied the convergence of the maximum. So, and Madol, Rod, and Vargas, that's the work I mentioned, studied the convergence of the Gibbs measure. And they obtain really a complete description of the limiting object. That means they have the real convergence of this Gibbs measure, but they also obtain information, the spatial information about the atoms. So that's very nice work. And I should also maybe mention a very nice survey by the same author, Duplantier, Roche, Sheffield, and Vargas, which is called log-correlated Gaussian fields, I guess. An overview or a survey, something like that, where you can, it's nice to learn about the continuous model. Okay, thank you very much. I stop here.
Is what you're doing in this work fundamentally two-dimensional, or is it sort of true if you have a log-correlated field in arbitrary dimension?
No, before that we did it on another model which was very, very simple. And Fyodorov and Bouchot introduced, they wanted to apply random matrices techniques and introduce a one-dimensional log-correlated Gaussian field defined on the circle. So you can do that. And because you're on a circle, you avoid all the boundary effect. So the big, the work in this work, the big stuff to do was to control this boundary effect, and that's I try to explain here. But we already had this spin glass approach on this model, which is very, very simple. And you have this very nice cone representation. I don't know if you know that, but you can see you have a graphic that tells you what are the correlation between points. So you don't have to play with these.
But I mean, this would work also in dimension.
Any dimension,
yeah.
Yes.
And then the way you treat the boundary effects here is also, is this also something that's sort of universal, or, I mean, or is it really dependent on the fact that you're talking about the green function on the two-dimensional square?
No, I think it does not depend on the green function. When you work with the green function, what I did not say, but when you make comparison between the fields, you always have to control. You have some big O of 1 terms that differ from one side to another side, which you don't have in the Gaussian multiplicative curve, for example.
Any other questions? Okay, if not, then let's thank both our speakers.